Okay, so welcome back. So today's speaker is Martin Schlecker. Martin just arrived at University of Arizona and joining Stewart Observatory from Germany, from Max Planck Institute for Astronomy. He worked with Thomas Henning and Hubert Clark on exoplanetary systems. So he will give a talk about the architectures of planetary systems today. So Martin, the floor is yours.
Thank you. Thank you very much, Serena. Thank you all for coming and for having me. To those who don't know me yet, which might be most of you, since I'm still new at Stewart, as Serena said, I just recently completed my PhD. This was in Heidelberg, Germany. And just last week, I joined Daniel Arpaio's group as a postdoc. And I'm very excited to join the exoplanet community in Tucson. It's really a great pleasure also to today present some of the stuff that I have worked on in the recent past. Most of it is from my PhD at MPIA, from my PhD time. And obviously I didn't do this alone. I got help by a lot of people, and I list some of my main collaborators on the slide. And preparing this talk was also a great opportunity to identify a common thread of the different PhD topics that I've been involved in. And I don't know if I succeeded in doing this, but the story that I would like to tell you today is about the architectures of planetary systems, of multi-planet systems, and what this architecture can tell us about how the systems and the planets have formed. But before we get into it, I thought it would be a good idea to sort of give you a manual of this talk. The main theme of my talk is a comparison of observed and simulated planets. And so to make clear which is which, I thought whenever there's observed data shown in a plot or in an image, I will show a real cow as the upper one. So this image, if you see this in the corner of a slide, it's observed data. You might notice the cow is also slightly distorted. So this could be due to instrumental effects, just as it occurs in nature, or some detection biases maybe. But the simulated data will then always have a spherical cow in the corner, just so that you're not confused what you're currently seeing. Let's start with some real cows, I would say. In this plot that you have all seen many times before, each point, of course, is a confirmed exoplanet that has a mass measurement. So those are included there, and plotted as planet mass versus period of its orbit, or if it's an RV detected planet, its minimum mass. And I should point out that, as most of you will know, that this plot is highly affected by observational biases. Typically, more massive planets on closer orbits are, of course, easier to detect, and we have this region of low completeness in the lower right corner. And we can also identify different groups of planets, for example, 3 groups of giant planets, well, depending on how you count it, but I see 3 groups there. I see the hot Jupiters that are actually highly overrepresented. This comes from this detection bias. They're actually rare. And then there are cold Jupiters, which are much more abundant. And in between, there are also a few warm Jupiters, and they also seem to be genuinely rare. There's an underdensity there, but they're interesting objects to look at. There's also a group of low mass planets. This actually includes many subgroups. So the exoplanet demographers in the audience, forgive me that I will call them all super Earths and sub-Neptunes. And a whole subfield has emerged from interpreting these various structures that you can see in these plots. And you can learn a lot from these different structures, but what is often neglected is that many of these planets are not the only ones around their star, but they're part of a system, right? So for example, these 2 planets they could live in the same system, or there might be a resonant chain of small planets in a system, and there could be a super Earth and a cold Jupiter in the same system. And this might actually tell us something about the formation of that specific system. And we can also see from this, there is not only a variety of exoplanets, but also a variety of planetary systems. And we can not only measure properties of planets, planet level properties such as planet radius, orbital distance, planet mass, but we can also constrain their system architectures, right? And so the question is, are the two connected? Are the properties of planets connected to the architectures of their systems? And I will try to convince you that the answer is yes. And I will also suggest planet formation pathways that could try to explain this link. So one problem that we always have is that planet formation can rarely be directly observed. And one way of overcoming this issue, or at least mitigating it to some degree, is to investigate different formation pathways with population synthesis, so planet population synthesis. The idea or the concept is that based on carefully selected initial conditions and on the current theoretical understanding of planet formation, one simulates synthetic planet populations that can then be statistically compared to an observed planet sample. So one actually needs a model that can serve as a link between protoplanetary disks and their features, so the disks in which the planets form and the environment in which they grow, and the final planetary systems that we can observe with the known exoplanet detection and characterization techniques. The model that I've been using throughout my PhD was developed by my Swiss collaborators, in great parts by Christoph Mordassini at MPIA and in Bern. It's sometimes called the Bern model. And the key assumption of that model is that it follows the core accretion paradigm, which is currently, I would argue, the most accepted picture of planet formation. And in a nutshell, the underlying assumption of that is that you first grow a solid planetary core by accreting planetesimals, or also smaller particles that are often called pebbles. And once this core is massive enough, it may accrete a gas envelope or an atmosphere. And depending on how efficiently this can be done, the planet then either ends up as a small rocky planet or as a gas giant. And then this happens typically at several locations in the disk, and you can get a whole system of planets. But once more massive planets form, they also interact with the disk, and this can change their orbits. We call this orbital migration. And in the majority of cases, this leads to shrinking orbits, so the planets migrate further in. But they not only interact with the gas in the disk, they also interact with each other. And so these orbital parameters that are set during the formation process, that can change, because these planets are not, singular isolated entities in their systems, but they do interact with each other. The problem again is that all these processes, we can generally not directly observe them. And so in order to close this gap that we're having between observations of disks and observations of planetary systems, so of course that we do what theorists like to do, we run simulations, right? And yeah, what I've shown you just now is of course a simplified picture, a model that aims to provide an end-to-end link between disks and planets, must actually contain prescriptions for all relevant physical processes, and then you can start long arguments, what are the relevant processes, what should be included and what not, given also that some of these physical mechanisms are only weakly constrained or cannot be directly observed. So it's a complicated, to some degree philosophical issue, but I want to highlight only some core components in our model that are included in our planet formation model, and also in its underlying assumptions, only the ones that are most important for the research that I present today to you. So let's have a quick look. So this will be only one slide to introduce the model to you. It's been continuously developed over the course of many years. And the current version combines a few key components. The first and one of the most important ones is that we model the evolution of a viscous accretion disk. This includes photoevaporation, so the disk is not only accreted onto the star, but material is also removed from high energy irradiation from the star, from the central star. And then we also have a module for external photoevaporation from other high massive stars in the cluster in which the system forms. A very important component is also the actual accretion module. We have planetesimal and gas accretion of up to 100 protoplanets that grow in the same disk. So pebble accretion is not included yet. This is work in progress, but we do accrete planetesimal accretion for the experts in the regime, oligarchic growth regime. And then we also solve for all of these planets the interior structure equations. This is very important when it comes to computing gas accretion rates, but also for the long-term evolution of the planets. And if you want to compute transit radii gigayears later, then you need to know what was the radius evolution of a planet. So for that, we actually, in our simulation, and this is one of the most expensive computations, actually, we do compute the radius structure equations at simulation time. I've mentioned before, there's orbital migration. We have all means by thinking that planets do interact with the disk, and they do migrate by doing so. And so there's two types of migration. I won't get into this too deeply, but the type 1 migration refers to the smaller mass planets, terrestrial planets, super Earths, which did not grow into gas giants, or not yet. Is typically a rapid and typically inward migration. Type 2 is then for the later stages of a gas giant planet. Once it has opened a gap in its surrounding disk, then we have a different migration regime, which we call type 2, which is usually much slower. And one key feature, especially for the smaller mass planets, is that we model the n-body interaction. So this really defines final system architecture. So as I said, planets interact with each other. We do keep track of these gravitational interactions. And as you're going to see in a little video that I made from just one simulation, there's a lot going on in terms of mutual interactions between these growing cores. And it's really a key component of our planet formation model. Then we have some compositional tracking. We do keep track of what material the planets actually accrete. And using an equilibrium chemistry model, we track the abundances of iron, silicates, and ice in the planetesimals that the planets accrete. Good. So I mentioned we're trying to connecting several things. And if we want to connect planet properties, the architectures of their systems, and planet formation mechanisms, we first have to establish links between the disks and the planets that emerge from them. And so in this project that was recently published, we tried to identify such links in our core accretion model. So the question was, what are the typical planet types that our model produces, and can we link them to certain disk features? So we ran our model in population synthesis mode, so to speak, where we randomly draw initial conditions of disks and starting positions of planets in the disk, and then we simulate a large number of systems to compute a synthetic population of planets. So we have to solve two tasks now in order to figure out these connections. The first one is to identify typical planet types in our population. And then secondly, we want to link disk properties to these different groups of planets, to these different planet classes. And the first part of the project is basically a data mining task. We searched our population for groups of planets that occupy similar regions in the parameter space of planet parameters. And we did so by means of a cluster analysis. At the end, we wanted to know how many clusters are in the data and which data points, which planets belong to which cluster. So a cluster in this sense is a planet type, a specific group of planets. And so for this task, we chose 3 typical exoplanet observables: the planet mass, planet radius, and the semi-major axis of their orbits. And we did the cluster analysis using a Gaussian mixture model. So what does this do? It assumes that there are several groups in a parameter space, and they can, so the data points can be drawn from multivariate Gaussians, and tries to find which are the best fitting multivariate Gaussians to draw these different groups that are detected. And then you figure out which data point or which planet belongs to which cluster or group. And we found that in the single planet approximation, the best performing model is a Gaussian mixture with 4 components of 4 different planet types. And in the multi-planet case, we find 5 different components. And I'm aware that we of course need the multi-planet case. This is the much more realistic scenario, but still I would like to focus a little bit on the single planet population first, because there we can really see nicely the structures in the parameter space well, and we can also understand better how this algorithm works and why the planet clusters are detected as they are. So this rather colorful plot shows different projections of the same parameter space. So let me walk you through this. This is simply in this planet radius and mass and semi-major axis space. These are all the different projections. And each point here is a planet that lives in its own system. So again, this is now a single planet approximation, 1 planet per disk. And yeah, I could talk an hour about the many details in these plots. So yeah, why lines or blobs separate from each other. So for example, there is a nice photoevaporation valley. I don't know if you can see my pointer. In the radius distribution, so this separates super Earth and sub Neptunes with significant envelopes, and can also see how in the mass radius diagram of these simulated planets here, where the giants are, how the radius flattens off once their atmospheres become degenerate. So there's a lot of interesting detail in this plot, but the point that I want to highlight is that the model, so this clustering model, seems to differentiate between different planet groups, so that seems to work. And interestingly, these planet types more or less correspond to the observed ones. So again, we did not presuppose any planet types. The planet clustering algorithm doesn't know anything about planet demographics, what planets are to be expected, or planet formation models or anything. It just looks for under and over densities in this parameter space, and these are the planet types that we're getting. So this is based on simulations at 5 gigayears. So we look at the outcome of the simulations at 5 gigayears, but we also asked ourselves if we can trace these clusters back in time, trace them all the way to the disk initial conditions, because we still want to establish this link between disks and planets. And so one can reformulate this as a classification problem, where the question then is, can we predict the planet species for a given instance of a disk feature? So give me a disk which has a size, a mass, I don't know, a dust to gas ratio. Can I predict from there which planet type comes out? So not running the formation model and letting it compute on a cluster for several weeks, but once we have understood the links in our model, can you just give me an instance of a disk and initial position of a planet embryo, and I will tell you what planet comes out. And thanks to the cluster analysis before, we do have labels for these instances. Each disk because we ran it many times, so we know which disk turned out to provide which planet type. And so we can use these labeled data as a training set and train a classifier on it that then hopefully predicts the cluster of a new instance that comes without a label. And for that, we used an algorithm that's called random forest. So it's really, I don't have time to explain it in detail, but it's rather nice because it's simple. It's called forest because it's composed of many, many decision trees. So it's really simple. It looks at different features, input features. So in this case, disk mass, disk radius, and such things. And then it decides where to turn. So it's I'm happy to chat with you afterwards. If someone interested in the technique, it's rather neat. But the only thing that you need to know is that it works as a classifier where we give it as input features the initial gas and solid disk mass, the initial orbital distance of the planetary embryo, and the lifetime of the disk. Which, if you're strict, it's not an initial condition, but we thought it might be very important for the outcome, because the lifetime of the disk is really what sets the time window for planet formation to happen. And once the disk is gone, not much happens anymore, which is not entirely true. There's a long-term evolution, but accretion is over and you would not turn a Neptune into a gas giant anymore. So we included lifetime of the disk as well. And we found that this random forest can indeed predict most of the planet clusters correctly. The accuracy based on data that these trees in the forest have not seen during training was 98%. And interestingly, when we switch on the n-body, which of course introduces a lot of stochasticity, we still obtain 89%. So that's great. We can get rid of our planet formation model. No, of course not. This doesn't tell us much yet about the kind of errors that the model makes. So I was actually most interested in what is with the other 2% or the other 11%, the cases where the classifier was not able to predict which planet type comes out of it. And we can look at these mistakes of the classifier in a confusion matrix, where for each actual cluster, so here on the vertical axis, I have the actual cluster of the planet, and on the horizontal axis, the predicted cluster, the cluster that was predicted. And most systems here fall on the diagonal, so that means, of course, a correct classification. But it's interesting, again, to see where the model is wrong. And we see that misclassifications are typically neighboring planet types, so neighboring in the parameter space, which here I'm showing you the radius semi-major axis space where these different clusters live, and usually they're confused. So neighboring, in this plot, neighboring planet types are confused with each other. So for example, the cluster 2, which are these icy cores out there that did not grow significantly, they are often confused with cluster 3, which are the giant planets. So some planets forming on distant orbits are apparently at the brink of becoming gas giants. And in the paper, we find some rules or thresholds in the parameter space for this decision. But what I wanted to show you here is also the multi-planet case. So here, as expected, it looks a bit more chaotic, especially also in the scatter plot in the upper right. You see that there's less structure than before, because now planets interact with each other. There is additional chaos in the mathematical sense introduced by n-body interactions. And now in the confusion matrix, we see that Neptune, so this is cluster number 1, and super Earth, cluster number 4, these misclassifications are actually not symmetric. You see there's 3% in one direction and 9% in the other direction. And the reason is that giant collisions happen between these planet types. So some of the Neptunes collide with other planets and turn into super Earth because they're losing their atmospheres. And this, of course, relies on the n-body effects of the stochastic effects of the n-body, and this cannot be predicted from initial conditions. And the conclusion from that is that these giant collisions have to be taken into account in information models. We cannot rely on theoretical prescriptions anymore that would just predict the radius of a planet, because we don't know if a collision might have happened and removed the atmosphere of a planet. So this is one of the results that we need to model these giant collisions between planets. And if we want to look at which parameter is actually responsible for the properties of a planet, so which initial conditions, which disk feature, we can look at something that in machine learning language is called feature importance. And what it is it tells you how important a feature is for a correct classification. So this is a complicated value here, this mean decision boundary, but simply put, what it tells you is that if it is small, then, or the amplitude tells you how important the feature is, and then the sign, so in which direction it goes up or down, tells you if small or large values are preferred. And so from this plot, you can see very clearly that the variable that most strongly defines what type of a planet will be built is the location where the cores form. So this is the initial placement, initial orbital distance of a planet embryo distance to its host star. So synthesis of the next generation of models should recognize this by including self-consistent treatment of planet embryo formation. This is what we're currently not doing, but my colleague Oliver Völkel at MPIA in Heidelberg is already working on this, so that we also now take into account these earlier phases of planet formation, including dust evolution and all the necessary parts that will actually give you the planet core to start the further processes with. So some key takeaways from this part. Our goal was to find links between disk properties and typical planet species in a population synthesis model. We did then a cluster analysis on our synthetic planet population, and we found that we can robustly predict what planets form, but gravitational interactions between the planets change the outcome, especially when giant collisions occur. The property with the most predictive power turned out actually not to be a disk feature, but the starting position of our planet cores. And what was also surprising to me is that the lifetime of the disk did not play a significant role. Okay, so with the disk-planet link established, we can turn to system architectures. We can quickly recall these different planet types that I have introduced in the beginning. So in this second project, we were actually interested in two particular planet types: super Earth or sub-Neptunes on close orbits, and giant planets far out, or cold Jupiter. So these two planet types that I highlight here. And if you try to label them in mass radius or mass period space, there's no universal consensus. Of course, we adopted these limits that you see here from observational studies that we wanted to compare our simulated planets with. The one thing that was important for us is that we distinguish between gas giant planets and the rest, and also between close and far orbits. So these observational studies that we wanted to compare our simulations with, they found a very interesting trend, because they counted numbers of systems that had either one of these planet types or both of them detected, and they found that there's an enhanced cold Jupiter occurrence in systems that also have a super Earth. So mathematically, this means that the conditional probability of having a cold Jupiter, given that there's a super Earth in the system, is higher than the probability of finding this cold Jupiter in any random system. And it also seems to go in the other direction. So given there's a cold Jupiter in the system, it's more likely to also find a super Earth in the same system. So it seems that I don't want to say emergence, but the presence of the planet types, or at least their detection, is somehow mutually beneficial. So that doesn't mean that really the planets influence each other. It could also mean that they just rely on the same beneficial planet formation conditions in the disk in which they grow, and in another disk we don't get either of them. And of course, there are all kinds of observational biases involved, and so the actual numbers are debatable, but a non-correlation case or even an anti-correlation between these planet types seems already to be excluded. And so we were wondering what happens in the simulations. Can we establish the same trend, or what's going on there? And I would like to show you just one simulated system that is sort of representative of a rather interesting phenomenon that we have seen in our simulations, where we try to do the same, count super Earth and cold Jupiters. So in this little video, once I'm starting it, you will see so this is one single system, and you see here semi-major axis mass, and each point is a planet. So we have a lot of planets in the same system. We start with initially 100 lunar mass embryos that then accrete simultaneously. And they also leave tracks in the plot. So I've already had it running for a couple of 100 years. We have these vertical tracks, which would mean that the planet grows but does not migrate. At some point, you'll see that the tracks turn horizontal, and this then means that planet migration is happening. And we will also see that some planets will be lost on the way because they interact with each other. They collide, they eject each other, and then you see a little a gray X where a planet ends its life. And the color code is then water ice mass fraction in the planet core. So this will also be important in a minute. So let me start this and see if hopefully you can see this on your screens as well. So we see already that planets interact. Some get eccentric. These horizontal bars that are popping up means the range of an orbit. And let me just, sorry, to restart it. Just wanted to take a break somewhere in between, because around here we can see that at least two of these planets grow rather efficiently. So they have clearly, or are about to enter runaway gas accretion, and they grow into gas giant planets. And we have a few smaller inner super Earths as well. So here's a system of planets, Earth, and a few super Earths, and a few giants at around a couple of AUs. So we see this configuration rather often. But if we continue the video, we see, and now you have to watch closely, that these giant planets scatter at some point and end up on eccentric orbits. And at that point, they excite the inner system and basically completely destroy it. We can watch it one more time because it goes very quick. But at the end, after these giant planets, all gone, become eccentric, we basically only have these eccentric giants left. And we do see that super Earths form in nearly all systems that host such an outer giant, but they are then frequently removed by such dynamically active warm Jupiters. And then, of course, we ask ourselves, do super Earths with giant companions differ from those without? So those that still have giant companions in the system, those super Earths that did survive. And to address this question, I divided the population into two different groups of systems, the ones that contain both super Earth and cold Jupiters, and the ones that contain only super Earth but no cold Jupiters. So here I plot each of these groups in semi-major axis mass space and color-coded again as the fraction of water ice in the core. And you will know in a minute why I focus on this water fraction so much. We did find that on average, super Earth with a giant companion have actually a lower ice mass fraction than the ones without. So there seems to be a connection between the architecture of a system and the bulk composition of the planet. At least this is what our model tells us. And then, of course, you may ask, can we actually test this? Well, if you have different ice fractions, you do get different bulk densities. And so these planets should show up in different positions in the mass radius diagram. And so we can turn this argument around and say, if you detected a super Earth, can you use its position in the mass radius diagram to learn something about possible additional planets, to maybe predict if there should be a giant planet in the system or not? And so if we plot these same two different populations in a mass radius diagram, and here I'm plotting only the super Earth, we see that indeed they do occupy different regions in the plot. So these prominent two diagonal lines here, they correspond in our model to rocky and icy cores without the significant atmosphere, so they follow nicely this diagonal part. But we also see already that there are almost no icy ones in the population with a cold Jupiter, so this is the upper panel. And the difference between these two populations of super Earth is even more evident for planets with atmospheres, because there we don't see this cloud of ice-rich and atmosphere-bearing planets in the systems with super Earth and the cold Jupiter. That means there is a link between planet composition and system architecture, which is an interesting prediction. And of course, we wanted to check if it's real. So we compared it to observed exoplanets. And so this is only the sample of super Earth in systems with super Earth and cold Jupiters. So observed systems with both planet types. The problem is that the sample with super Earth and without cold Jupiter is corrupted by biases, because there could still be cold Jupiters that are undetected. But if we overplot it, we see that it already fits the corresponding synthetic sample, and it does not fit the complementary sample. So here, in other words, we get a better fit for the corresponding synthetic sample than for the complementary synthetic sample. I know it's way far from unequivocally proving the prediction, but the sample in mass radius in this diagram is, of course, increasing rapidly with current and future missions. And until then, until we can really falsify or prove this prediction, we can at least use our model to try and understand how this effect should come about if it exists. And I found that rather interesting. But if we go back to different disk initial conditions, I told you there's disk mass and radius and dust to gas ratio and other parameters, but the defining parameter was really for this effect the solid content of the disk, which is distributed differently for the two populations. If we plot the cumulative distribution for these familiar two groups, then we see that systems that produce a super Earth but no cold Jupiter started typically with intermediate mass disks, so maybe 100 Earth masses in solids and planetesimals. And systems that produce both planet species, they had a more massive disk. Let me try to connect the dots for you in a little cartoon. So we have two cases. The first one, intermediate mass disk, it still has to be sufficient for planet formations. We need around 100 Earth masses in solids in order to form some super Earth. In this case, primarily icy super Earths form just beyond the ice line. They migrate inwards and become systems of volatile rich planets. We can measure them. They have low bulk densities, and we don't see any giant planets. In the second case, where we have a rather high mass disk, several hundreds of Earth masses in solids, we can form cores further in as well. They migrate inwards again to become dry super Earth, but the conditions are also right to form giant planets. And these giant planets sitting in there, they would prevent any icy cores that would form further out from migrating inwards into the inner system where they would be detectable. And so in the end, we have a system of high density super Earth plus a distant giant planet or two. Before I finish, let me quickly touch on the implications for planet formation if this mechanism really works the way we see it in the model. The observations and also our planetesimal accretion model predicts a positive correlation between super Earth and cold Jupiters. But on the other hand, some pebble accretion models, so models that not only accrete planetesimals on the planets, but accrete their solids also in the form of small particles that tend to drift through the disk and are very efficiently accreted. They would predict an anti-correlation here. So we could maybe use this effect to constrain the efficiency of pebble accretion versus planetesimal accretion, but also the timing of when giant planets emerge in the system. Another aspect relates to planet migration. As we've seen before, we find that outer giants and inner super Earths do form together whenever the conditions are right globally in the disk. And where super Earths are missing, these systems are usually destroyed by dynamically active giants that migrated inwards and became warm Jupiters. So one typical observed example of this is TOI 2179b. This is a very eccentric 15-day orbital period warm giant planet that we have discovered with test data. And indeed, we found that no stable orbits interior of it for any super Earth is possible in this system. So this might be one example of such a highly dynamically active giant planet. And who knows, maybe there was a nice, beautiful system of super Earth in the system before, but it was removed by this rather aggressive intruder. But as we have seen, I just wanted to remind you, we've seen before, these objects are rather rare, so they're much rarer in the observed population than in our synthetic population. We tend to form too many of these warm Jupiters that are at intermediate distances. And this again might be a hint that planet migration is not as efficient as proposed by our theoretical prescriptions. So I want to finish with just a few takeaways of my talk. The first is that in core accretion theory, the orbital distance of a planet core is an important predictor for the emerging planet type. And the disk mass also defines the architectures of the resulting systems, not only the planets and their properties that form. We've seen that in intermediate mass disks, icy super Earths form, but no giants. And in rather massive disks, rocky super Earth and giant planets can form. The super Earths are then often destroyed by eccentric warm Jupiters. Super Earths that do have a cold Jupiter in the system are on average less icy than field super Earths. That's the prediction. And this then leads to the prediction that those super Earths with a high bulk density might be used as a proxy for giant companions in the same system. And so with this, once again, thank you for having me. It's been a pleasure to present some of my PhD research to you. And yeah, thank you all for welcoming me so nicely at my first week at Stewart and on the campus at UA. I'm very excited to be here and I'm happy to take any questions now.
Okay, thank you. Thank you, Martin, for your wonderful, exciting talk. So if you have any question in the audience, please you raise your hand. Now is the time. Okay, Robert.
Yeah, I just wanted to know a little bit more about the current state of giant impacts in the M-body simulations, whether perfect merger accretion is being used. I know that there is recent 2019 onward like machine learning models by like Sergio and like Emsenhuber that do a little bit less perfect accretion models that might be interesting. I don't know if you've been looking into that.
Yeah, it's certainly a very good question, but you're asking the wrong person. So for the merging events and these collisions, of course, Alexandre is the person to ask. But what I do know is that in the way we handle it in this current formation model, the version that I've been using for my studies, the important feature that we were looking at and that led to these different predictions was that the atmosphere got removed. So this is something that typically happens if you have giant planets colliding, and you could model it in different degrees of detail. As far as I'm concerned, and as far as I know, this specific module of the monster of a model that we have, we remove the whole atmosphere of a planet if a certain energy was exceeded. So it's kind of a binary process where either the atmosphere is removed or it stays. And this, of course, can be improved. And Alexandre is looking into improvements of this where only parts of an atmosphere can be removed. And also in the different outcomes of a collision event. When do you have a hit and run? When do you have a merger? So there's certainly rooms for improvement there, but we can already tell from the statistics that I've shown you here that it's an important component that we do model these collisions.
Okay, so next, I think Joanna somehow quit. So Max, you can turn on the video, Max.
Oh, yeah. Hi, Barton. Great. Thanks for the talk. Can I ask what you mean in terms of your main takeaway here, intermediate mass disks versus massive disks? Is this at the time of the formation of the embryos, or is there some correlations with the final host mass of the star, of the host star? The reason why I'm asking is we only see that correlation between close, super sub-Neptunes and cold Jupiters for solar type stars, but for M dwarfs we only see the close-in planets, not the Jupiter. So is that your assessment as well, that solar type versus M dwarf comparison?
Right, thank you. So I'm realizing that I've important to mention something really important. All I've shown you is solar type stars. So the simulations all assume a one solar mass host star at the center. These variations in disk mass, they come from running our formation model in a population synthesis approach. So it's a Monte Carlo process where we draw initial disk masses, initial solid disk masses, but also initial gas disk masses. We do have and I've not shown this here, we also have versions of the model that have varying host star masses. We're looking into M-dwarf simulations lately a lot. So this is work in progress. And there, of course, the disk masses also scale with host star mass. But what I've shown you here, this basically assumes the same host star masses for all simulation, and we just vary the disk simulations from within a range where we think it's realistic based on observations of disks that are out there.
Yeah, interesting. Great. They get this much variation even within solar types. Great. Awesome.
Sorry for the confusion.
Okay, Nienke.
Hi, Martin. Great talk. And thank you. So I just wanted to follow up on the previous question. Because I was thinking along the same lines, because so me and Gijs Mulders, we had a paper last year where we showed that there's this stellar mass dependence of disk showing substructure, so possibly caused by giant planets, and like an opposite one for the compact disks, maybe related to the super Earth. So that would essentially, we're predicting an anti-correlation. And yeah, so I was really wondering how that fits in with your model and how easy it is to add sort of occurrence rates of different stellar masses and different disk masses, initial disk masses. Because I think that would make the whole model much more comparable with what we're seeing in the disk observations.
Yeah, so good point. We did do this in at least focusing on M-dwarf systems in a recent paper by Remo Born. So Born et al. There we show the numbers of different planets that we get if we simulate M-dwarf systems. We downscale also the disk masses, and then we also compare it. That's now the next step with observed surveys of M-dwarfs. And there we actually, so this is already submitted, but work in progress. We see something actually pretty confusing, that we also get giant planets in the observations. We see some giant planets around lowest mass stars. One example is GJ3512b, Morales et al. To those who know it, this has been very surprising, but it's not the only type of these giant planets around the lowest mass stars. And this we cannot reproduce with our model, but we found that this actually works better. We do get giant planets even for lower mass disks and around low mass host stars if planet migration is inhibited. So we apparently have a too efficient way of migrating our planets. So they run into the star before they can grow into giant planets. And one reason, what I suspect is the reason for that, is that we still assume these smooth disks. We don't have any substructures in the disk. So this is, in my opinion, one big weakness of the model, that we have an oversimplification of the disk structure. It's just a smooth power law disk. Whereas I'm familiar with your paper, you assume also disk structures, and this would then also, of course, change the migration behavior of planets.
Yeah, there's also I've read quite a bit of work on migration recently, and there's quite some evidence that low viscosity really changes the migration. It may even turn it outward, or at least slow it down. And also Kanagawa et al. Has a new prescription for the type 2 migration, because if a planet carves a gap, it is essentially type 1 migration, but then the gas surface density inside the gap. And I think all of these new prescriptions are not yet taken into account. I don't know, you were just citing Particle, so I'm assuming you use the classical prescriptions. So I think these are possible updates for that. That may solve that.
Yeah, indeed. I think that's one issue that we typically have with planet population synthesis and these global models. We're trying to keep up with new developments, but we also want to include only the prescriptions that are to some degree established. And then it takes us months to run our population.
For sure. Yeah, I understand. Yeah.
We're always running behind. That's one issue.
Yeah. Okay. No, well, I'm looking forward to read your papers. And if you want to know more about the disk structure, feel free to reach out. Thanks.
Yeah, great. Thank you, Nike.
Okay, so we have some question in the chat. So Sergio best. Sergio, if you'd like to ask question in person, that would be great. Sergio asks, do simulations start with class 2 disks? What happens if planet formation starts in class 0 or 1?
Yeah, good question. So we did change the assumed disk masses to the Tichoniet's paper, which doesn't look at type 2 objects anymore, but type 1. And so the disk masses are now higher than before. This, of course, helps us with planet formation, but they can also influence, again, planet migration. So it is one thing that that could worry you, or that's reassuring. I don't know. In planetesimal accretion, we still have this pure planetesimal accretion model in terms of solid accretion, and this can only be efficient enough if you get to high enough local density of solids. We don't have pebble accretion included, not yet. This would help with growing planet cores more efficiently, but until now we're limited to having high enough solid densities. So what I'm looking forward to is having actually both compared and trying to compare what we get with pure planetesimal accretion and pure pebble accretion, and then having at some point both implemented and being able to see what the combined effect of them is.
Okay, so that's a complex problem, and good luck with that. Actually, adding the earlier stage disk evolution. So next question is from Yasuhiro as Hasegawa. Yasuhiro, if you would like to ask a question, you can turn on your video and ask as well.
Oh, okay, yeah, I'm gonna ask you the question directly. So maybe maybe some of your group member already compare, but then I'm just wondering that did you compare the mass or radius relation of your result compared to the observed one, say chain keeping 2017, and then did you see any difference or similarities or?
Well, we did. I think I've shown a figure before showing this. I don't know if you refer to this plot where we did actually overplot the mass radius measured planets. So these are only the super Earths, of course, but here, yeah, this difference in these two different populations, depending on the architecture of the system, becomes apparent. And the rest, well, there are of course large arrow bars in the observations, but the rest seems to my view seems to overlap quite well. I don't know if this was your question.
Oh,
but
no,
we do, yeah.
Yeah, that's the kind of things I'm looking for. But then I'm really looking for the slope of the relation. And then do you think you can reproduce the slope of the correlations, or maybe it's
yeah, now that you say it, it might be a bit deeper in the observed system, but yeah, of course, in the simulations, it's easy to tell where you get these nice straight diagonal lines, and we know these are the ones without any atmospheres. We don't have arrow bars. It's easy to measure it. But yeah, I didn't specifically look at this yet. This was not part of this comparison, but it's actually an interesting idea to see where these slopes deviate, and if it's still in the, within a standard deviation of slope or not. So I don't know if Alexandre looks at this in his paper, but could be. I mean, this is certainly one feature in the demographics where we learn something about our accretion formalism. So yeah, thanks for that input. Yeah.
Okay, yeah, great, thank you.
Any other question? Okay, if not, let's thank, you can unmute everyone and you can turn on video as well, and thank Martin for a wonderful talk. Thank you.
Thank you.
Thank you all for coming. Thank you.
Yeah, we'll see you next week.